we sort of did this really easy derivation for the field at the center of a charged ring. And if we think about adding up all the electric fields, they just go to zero. We're going to look at the electric field due to several different shapes or continuous lines of charge. These are shapes where you have a charge that is evenly distributed across that shape. Now, if we have distinct point charges, like we've been doing, where we have 3 or 4 point charges and we don't know the electric field, then we just add up the electric field, do the vector addition. But if we have a continuous line of charge, then we divide the object into differential elements, and then we integrate to find the total electric field. So we're going to divide each piece up into little bitty pieces of charge, dq we'll call that, and then we'll integrate to find the total electric field. Now when you do the derivation for the electric dipole, there are only 2 objects there, so you don't need to integrate, but you have to do some approximations with the binomial theorem in order to develop an expression for the electric field of a dipole. So either one of those, you want to do the dipole or the disk, is fine with me. So we're going to consider 3 configurations: dipole, that is an equal and an opposite charge, a plus q and a minus q together. We'll also look at a charged ring, which we're going to do today. But different from the charged ring that we did very simply, right, where the charged ring, the electric field in the center was 0. We're going to look at a point up above the charged ring, and then also a charged disk. And when you do the charged disk, the easier way to do that is to take the results from the charged ring and then use them to find, you'll integrate over that charged ring in order to find the results for the charged disk. We've done that before. We did that last semester when we did the moment of inertia, integrating to find the moment of inertia. Remember, we found the moment of inertia of a hoop, and then in order to find the moments of inertia of a disk, then we let that hoop be our differential element, and then we summed that over the surface of the disk. Just sort of vaguely remember that? Yeah. If you don't, you can look it up online. That's sort of the typical way to derive the moment of inertia, or excuse me, the electric field due to a charged disk, or the moment of inertia. It basically works out the same way. All right, first we want to just define some quantities that we use. Charge, we already talked about. The symbol is Q, and the units are coulombs. But then also we have charge densities. We can have a linear charge density. That is how much charge along a line, how many charges per unit length. And then we can also have a surface and a volume charge density. So the linear charge density will be how many units of charge per unit length. The surface charge density will be how many units of charge per unit what? Not length, but what's the next step? So I want to know how many units of charge along a certain length of material, or along a surface, then it's going to be units of charge for what? Per area, or meters squared, right? And then volume will be our meters cubed, right? So this is going to be, the symbol for linear charge density is lambda. For surface charge density is the lowercase Greek letter, what's that, sigma? And for volume will be rho, which is our typical unit for volume density. But this is a charge density. So as we've already said, this is coulombs per meter. This is coulombs per meter squared, and then this is coulombs per meter cubed. And we'll use those as we go about in the derivations to express the final electric field for our particular configurations. All right. That's it. I'm going to go ahead and skip the dipole. That's going to be one of those that you'll turn in for your test. I haven't decided how much it's worth. Probably about 10 points. Yeah, let's say 10 points. That seem fair? Yeah. So spend some time looking for that, or you're working on it on your own. You will need to use the binomial theorem in order to find the dipole. let's go ahead and do the ring, the charged ring. I want to find the electric field at a point P, which sits up above the charged ring. So this is a 2D picture or a 3D picture where I have this ring that's sort of coming out of the page, and then at a point in the middle of the ring, I have a point P that comes up right in the middle of it. The ring has a radius big R. The height above the ring is a distance Z, and then this distance is a little r. All right. So first, I want to consider the charge element. So if I think about this differential element ds, it has a charge dq, and I can express this in terms of lambda as lambda times ds. So remember, ds is, or excuse me, lambda is our linear charge density, coulombs per meter, and then if I multiply this times this length, this is just a measure of length, ds, then that gives me my value dq. You with me on that? Yeah. So that gives me the charge of that differential element ds. And so I want to define my electric field dE. Remember, E is kq over r squared. So dE is going to be k times dq over r squared. Well, I'm just finding the electric field due to this little differential element. And then I can express my dq in terms of lambda and ds equal. So dE then is just equal to k lambda ds over r squared. All right. I can rewrite this value r in terms of z and big R, because notice I have a triangle here. So I know then that r is equal to the square root of z squared plus r squared. So I'm going to say then that dE is k lambda ds divided by z squared plus r squared. Right, because if I take the square of this, that should be a big R squared. It's right here. All right. If I look at the electric field due to this point, I can imagine a bunch of vectors. I have vectors that are going in this direction and in this direction, and then all the way around I have those vectors that will add up. See, so for example, due to this element I have a vector in this direction, due to this element I have a vector in this direction, and then those vectors are going to go all the way around such that they're going to either add up or cancel one another out. Which components will cancel out? Now these vectors have two components, they have an x and a y component. Which component will cancel out? The x components will cancel out, right? So the ones, I have one component in this direction and one component in that direction. And so the only component that's going to be left is the component that's pointing up. So the y component will be left. So really what I'm looking for here then is my dE cosine theta. So dE, the only thing that's left then is going to be dE cosine theta, and that's going to be the component of this vector that points up. I know usually we say that cosine theta is our x component. Yeah, Daniel? Okay. Usually it's our x component, but because of the way that I'm defining this angle theta, it turns out that the cosine of this angle theta gives us a y component. Because we're not defining our angle theta in the normal way that we should do. That is not from the x-axis. Instead, we're defining it from the y-axis. Is that clear? All right. Okay, so we know that the definition of cosine theta is z over r. Right, that's adjacent over hypotenuse, which we can also write as z over z squared plus r squared to the 1/2. All right, so we can now rewrite this where we have dE equals k lambda ds divided by z squared plus r squared. Right, that's just what we had up here. And then we're going to multiply by this cosine theta term. Z over z squared plus r squared, square root of that. Alright, we can simplify this, and then we'll just take the integral. So let's see, how does this simplify? dE is k lambda z ds divided by z squared plus r squared. What's the power on that? What is it? I have a power 1 here and a power half here. 3 halves, right. Alright, did I get everything there? K lambda z ds. Yeah, so I'll just sort of combine it all together. Now I want to integrate over ds. And which of these variables changes as ds changes? That is, as I move around the ring, which of those variables changes? Well, k and lambda are constants, right? So really I'm just looking at z or r. How do those change as ds changes? That is, as I'm moving around this ring, I start adding up this quantity, taking the integral. I start adding up that quantity as I move ds from here to here to here and all the way around the ring. And so I want to pull out those variables that aren't dependent upon ds. So these variables that are constant, I don't need to integrate over. So which of these variables are constant as ds changes? K and lambda we know are constant. Those are just physical constants. But what about z or big R? How do those change as ds changes, as I move around that ring? None of them change, right? They're all independent of ds. So I can take everything out of the integral, and so all I'm left with is the integral of ds, which is a really simple integral to do, because it's the integral of ds. And then what am I going to integrate over? So ds starts at 0, but then it goes around to another value. What does it go around to? What's the, not 2 pi, but what? Right, we're not integrating in a, what's the word? I forget the word. What's the word for when you like integrate radially? Yeah, y'all know what I'm talking about, right? I can't remember the word. But anyway, we're integrating over a line. It's a line that's in a circle, but it's still over a length of the circle. Alright, so I pull out everything, and the integral of dE is E. That's what we're looking for. K lambda z over z squared plus r squared to the 3 halves, and then the integral of ds. And as you said, I'm going from 0. Is it 2 pi big R or 2 pi little r? Yeah, 2 pi big R. That's the radius of my ring. And then I put that in. 0 to 2 pi r is just 2 pi r. So I'm left with k lambda z 2 pi big R divided by z squared plus r squared to the 3 halves. That's going to be my electric field. And then I can simplify this further, because notice if I multiply lambda and 2 pi r, if you recall, lambda was equal to the total charge, q, divided by the total length. So it's going to equal to q over 2 pi r. So if I multiply lambda times 2 pi r, I'm just left with q. So E then will equal to k z q over z squared plus r squared to the 3 halves. Alright, and then that's the answer. That is the electric field at some point above a ring of charge. We can also make some approximations. So let's say that if z is much, much bigger than r, that is, if I'm really far away from this ring, if I sit at a point very high above this ring, what does that ring of charge look like to us? if Z is much, much bigger than R, if this value is a lot bigger than this value, right, so in the bottom, I get, this basically just goes away. This becomes irrelevant. So I get a Z squared to the 3/2, or a Z cubed, and then I'm left with a KQ over Z squared. You follow what I mean by that? If Z is much, much bigger than R, what happens there is this R squared becomes irrelevant. It basically goes to 0. We can think about it in that way. And I'm left with KZQ over Z cubed. Z squared to the 3/2 is Z cubed, which is just KQ over Z squared. Alright, so if Z is much, much bigger than R, our electric field looks like this. And this is the expression of what? Electric field for what? Not a cylinder, no. A point charge, yeah. So if you're really far away from this ring of charge, it looks like a point charge. That should make sort of sense, right? I mean, if something's really far away, it just looks like a point. If you're closer to it, your electric field looks like this. But when you're really far away, it goes down to a point charge. So if really far away, the ring looks like a point charge. All right. So what I want y'all to do is take either the dipole or the charged disk and do the derivation for those, finding the electric field. And again, honestly, even in PChem, I'm not sure that y'all use this, but this technique of integrating over a surface is pretty important for a lot of different reasons. So it's a good way to go through these exercises. I'm not going to test you on it, but I'll give you credit for going through the effort of it. Okay? You understand what I'm saying? All right, so do those derivations for the test. One of them, it'll be worth 10 points on your exam. I hope it should be an easy 10 points. Everybody just bring it in on the morning of the exam, and you just hand it in to me. 10 points. It's free 10 points, right? Yeah. All right. So spend a half hour, find the derivations of those. Now for the charged disk, you're going to start with the expression of a ring, KZQ, rather, divided by Z squared plus R squared to the 3/2. So you're going to start there, and you're going to let that be your differential element, and then you'll integrate outward. Okay? I think there are a couple different ways to approach the charged disk, but this is probably the easiest way. Starting with the electric field for a ring, which we just derived, and then let that ring see your differential element. It has a radius little r, and it has a width dr. And then you can express the electric field in these, let's see, that. Yeah, in those. Yeah, this should say big R right here, I'm sorry. So here where it says Z, this should say big R. It's the radius of your charge disk. Right? You can do that, right? Look online. There's on Wikipage, on Wikipedia, they go through this derivation. There are some other, I think, Hyperphysics, a place out of the University of Georgia, they do this derivation too. All right? All right. I want to watch a little video. This is a video about, it's a TED Talk. You ever watch the TED Talks? Yeah, so this is a guy, Bill Doyle, I think his name is. He's a researcher, and he's using electric fields to treat cancer. So, anyway, it's for your own interest. We'll watch it. I think it's kind of interesting. Almost everybody here has been touched in some way by cancer, family member or friend or whatever. And he's talking about this interesting new way to treat cancer that doesn't involve chemo or radiation, or the usual harsh techniques that they take for treating cancer. In the human body, and in general for charges, because everything's made up of charges, but I read recently too that your bones use a lot. They when they generate new bone material, they do this process utilizes these electric charges that are in the cells. And to hasten bone growth, they'll do a similar thing where they'll take these transducers, these metal plates, and they'll put them around your bone, and it helps to speed up the bone growth in them. Well, I don't know if anybody's ever done that. Have you ever seen that or done that? No, I've never had bone issues, but they do that to help hasten bone growth. All right. See, we're not going to watch this about Michael Faraday, but Michael Faraday developed the idea of electric field lines. If you want to go online, you can watch it. You can search. It's part of a documentary called Einstein's Big Idea. Michael Faraday was in the century prior to Einstein, and Einstein said that he was like the most notable physicist of the 19th century. So he made a lot of headway in how we think about electricity and magnetism, and sort of paved the way for using electricity and generating electricity. We're going to talk about field lines, which he invented to show how to show the field lines. A couple different rules that we'll have. Field lines. The electric field is tangent to the lines. The field lines that you'll draw, and the magnitude of the electric field is given by the density of the lines. How many of you are not in lab, in the physics lab this semester? Just you, Josh? Okay. Well, y'all did a whole lab, so I'm not going to go into it here, but you can use the PhET simulation. Y'all done that lab where you did the computer lab for the field lines? That's this week? Okay, well, you're going to do a lab where you use a PhET simulation, a computer simulation, to generate electric fields, and then you play this really cool video game. Has anybody done it yet? It's a cool video game, huh? Do you like it? Yeah, so you'll use charges to move other charges around. It's kind of fun. So I'm not going to spoil the surprise for you, but I'm going to show you how to draw the field lines here. But you can do the same on this simulation. All right, whenever we have a positive charge, field lines go outward for the positive charge, and they go into a negative charge. So for example, a field line would start here and go here. Now I can imagine this field line, if I put in my positive test charge, it's going to feel a force away from this charge and towards this charge. Similarly, if I draw a field line here, it's going to look like this. If I were to put my positive test charge here, it would follow along this field line. In fact, do you remember the ping pong balls on the Van de Graaff generator? Did it work in this class? The ping pong balls, they all come out? Yeah, they actually follow pretty closely the field lines around this Van de Graaff generator, because you have this really big charge, and then they become charged, and they follow these lines of force as they come off the generator. So you're going to have field lines that look like that. And anywhere along these, if you put your positive charge, it will follow along that field line. Field lines are also called lines of what? Do you remember? Lines of force. Field lines are also called lines of force because that positive charge will feel a force along that line in the direction of the field. Okay, so at point A, the field lines are more dense, are closer together rather, than at point B. So the electric field at point A is what? Bigger or smaller than at point B? It's going to be bigger. It's bigger in magnitude. And if you remember, our electric field is kq over r squared. So if r is smaller for this point charge, then E is bigger. But that's represented by the field lines. If the field lines are closer together or more dense, then the field is bigger. So then the force that a positive test charge feels at point A is bigger than the force it feels at point B. And this comes back to our force is linearly related to our electric field. We define our electric field on the force. So whatever the electric field does, our force also does. All right, a few more rules. You could have a question on your test. It's not going to be worth a whole lot of points, maybe 5 to 7 points, that just ask you to interpret some field lines. I'll show you some questions that'll be similar in just a second. So lines for groups of charges must begin on a positive charge. So lines begin on a positive charge. And end on a negative charge. If there's an excess of charge, the lines will end at infinity. I'll draw you a picture in just a second. Or the lines do not end. They just go off into space. I'll draw you a picture in just a second. The number of lines on a charge is proportional to the magnitude of that charge. So a charge 2q would have twice as many lines as a charge q. And I'll draw you a picture of this in just a sec. And then 3 is, this should be apparent, maybe it's not apparent, but these field lines should never cross. I think it's cool just because it reminds me of Ghostbusters. Remember Ghostbusters? Don't cross the stream. Alright. So these field lines will never cross, because that would mean that if they cross, that would mean that you have two different forces at exactly the same point, and that doesn't make any sense. You can't have that. All right. So for our example, let me draw you some pictures to illustrate this. Here I have a plus q minus q. I've already done this, but it looks like this. Be prepared. You might have to draw field lines for certain configuration of charges. If I have an electric dipole, or this is an electric dipole, let's say I have a plus 3q and a minus q, then it's going to look like this. Say I have two lines that go into that minus q, then I will have 4 additional lines that go off into space. Alright, so I have 2 lines that end here. I have 6 lines that come out of here. So the number of lines that come out of a charge are proportional to the magnitude of that charge. So this charge has 3 times the charge of this charge, so it has 3 times the number of lines of this charge. We'll have some questions like this on the concept test next time, dealing with this. So that's from rule number 2.
So if there was 2 lines on the negative charge, it has to have
3 times as many, right. So if there were
total.
Right. So if there were 4 lines here, there would be how many over there?
12.
There would be 12 lines.
But only 4 would be lines.
Right, only 4 would be actually touching between the charges. Alright, so that's rule number 2. So plus 3q has 3 times as many lines as the minus q charge. And if I have 2 positive charges, like here, then the lines will look like this. And here, instead of having 2, I'd have how many on the plus 3q? How many, Courtney? 6. I don't know how you like. Right. In the lab, you're going to do some other configurations. Like, for example, you'll do 2 plates like this. We'll get into this quite a bit in a couple of chapters, where you have one plate that's made of positive charges and one plate that's made of negative charges, equal number of negative charges. And in this case, you get a very regular electric field that looks like this. We'll talk about these sort of arrangements when we get into voltage, because we'll talk about how charges move within this electric field. I think you'll also do a configuration that looks like this, where you have a positive and a negative like this, and your field lines will look like that there. If you ever want to ask yourself what are the field lines going to look like, just imagine if you have a positive charge and ask yourself what direction will the force be, and it's going to be attracted to this negative charge and repelled by the positive. All right, let's do this clicker question. We're almost done with this chapter. Figure shows two charges and their electric field lines. The charge on the left has a magnitude of 6 microcoulombs. What is the sign and magnitude of the right charge? And again, on the test, you might have a question. It won't be worth but a few points, but to just draw the field line for a configuration of charges, just like the one we've been doing. Nothing terribly complicated, just one charge here and one charge here. But what is the sign and magnitude of this charge right here? You can ask your neighbor if you like. All right, I'll stop about 125 or 130, let's say. Let's see, 1, 2, 3, 4, 5, 6. 130, I'll stop. All right, excellent. All right, yeah, so this is what is it, this is 6 microcoulombs, and because the lines are going into it, I know it's negative 6. And this one has twice as many lines, so this one must be positive 12, so B is the right answer. Let's do a few more questions these last few minutes of class we have. We'll wrap these up next time. By the way, I posted the Chapter 1 concept test on the website. I'll post these soon. Next time we're going to get into Gauss's law a little bit. This isn't in your book, unfortunately. This is one of those new chapters that I'm throwing in, and we're sort of going to see these throughout the semester. So I'll do like I did last time, where I photocopy my notes and send them to you. Does that help you? To have those? Yes. I'll have those done soon. Or at least after I get them done, I'll send them to you. Sorry, this is the wrong one. We've done all these about forces, is that right? Yeah. Okay. You're sitting a certain distance from a point charge, and you measure an electric field E naught. If the charge is doubled and your distance from the charge is also doubled, what is the electric field strength now? Don't forget, our electric field is KQ over R squared. I'm doubling the distance and doubling the charge. So what is my electric field? All right, I'll stop at, say, 55. 55. It's 10 more seconds. Y'all are doing pretty well. Most of you have the right answer. So ask your neighbor. All right, D is right. If I double Q, I get a factor of 2 in the numerator. If I double R, I get a factor of 4 in the denominator. So 2 over 4 is a half of what the electric field was before. So I have that linear and that inverse square relationship. Between the red and the blue charge, which of them experiences the greater electric field due to the green charge? So this one experiences an electric field at this location, This one experiences an electric field at this location due to the green charge. How do they differ? Or are they the same? Which experiences the greater electric field? Now let me remind you of something. Aren't doing real great on this. If this is my charge Q, then my electric field is KQ over R squared, or this is my distance R. So where is the electric field greater? Is it greater at this point, or is the electric field greater at this point? The electric field due to that green charge. Ask your neighbors if you like. You're doing a lot better. But just a few more seconds. I'm going to stop at 120. All right, good. You experience the same electric field. The electric field doesn't matter what this charge is. Now this charge is going to affect the overall electric field, but not the electric field due to this charge. All right. So the electric field due to this charge will be the same at that point, distance d from the green charge. All right. Have a follow-up to that. Which of these experiences the greater electric force? So we know that the electric field at the red charge and the blue charge are both the same. The electric fields are the same. But which of these charges experiences the greater electric force? Or you can think about this in terms of Coulomb's law too. Right? Now, the fields are just derived from Coulomb's law, so it's not incorrect to think about it that way. All right, I'm going to stop at 50 seconds. 50? Looks like we'll wrap this up. Very good. That's right. Our force is equal to Q times our electric field, so the bigger charge does feel the bigger force. Or you can think about it in terms of Coulomb's law. These two charges, because there's a greater collection of charges, will experience the greater force. Uniform electric field, an empty space, 4 Coulomb charge is placed and it feels an electrical force of 12 newtons. The charge is removed and a 6 Coulomb charge is placed at that point. What force will it feel? Think about what is the electric field that causes this force? Or your easiest way to go about this. All right, just a few more seconds. I'm going to stop at 55. Almost everybody has the right answer. 55, I'm stopping right now. Very good. He is right. What's the electric field that causes this 12 Newton force? It's what? What's the value of it? It's 3 newtons per coulomb, right? So 3 newtons per coulomb times 4 coulombs gives me 12 newtons. 3 times 6 will give me 18 newtons. You probably see a basic sport fields problem like that. You have some like it in your homework, sort of paired with a kinematics problem. All right, what are the signs of this? These last couple are real easy. What are the signs of the charges? This is green, this is red, green, red. You can see the lines come out of the red and go into the green. Just a couple more seconds. I'll stop at 25. Okay, excellent. That's right? B? Yeah, that's right. What side of the chicken has the most feathers? The outside. All right, which of these charges has the greater magnitude? Red, green, or green, red, or both the same? I think it's the last question. Yeah, this is the end. So. Red, green, or green, red, or both the same? All right, let's stop at 23. Excellent. All right, y'all. This is online for you, so you can download that. You can find the answers if you forgot or whatever. We'll start Gauss's law next time. As I said, that's not in the book. I'll send out the notes before class next time. Alrighty? Have a good day. Don't forget to get ready for that text, okay? Fields and forces are often difficult. Hopefully that's not the case for y'all. But let me know if you're interested. Courtney, you got my email?
Yes.
Okay. I think it's due today, is that right?
It's 2
Oh, good. Okay. All right. We'll give it some thought.
Yeah, I'm gonna look at it a little more today to see what is doable.
Okay. All right.